This section examines the principles of ignition. The ignition system provides a spark between the spark plug electrodes. The spark must occur at precisely the right time in the engine cycle, and it must have sufficient energy to bridge the gap and ignite the mixture under all operating conditions. The energy required can be obtained from the vehicle's electrical system, but the nominal battery voltage of 12 volts must be increased or stepped up to provide a firing voltage of many thousands of volts. This high firing voltage causes the spark gap to become electrically conductive, enabling an ignition spark to occur. It must have sufficient heat energy to ignite the mixture so that it can continue to burn by itself. Exactly how much energy is required varies according to the condition of the mixture and the pressure in the cylinder at the end of the compression stroke. With an engine at normal operating temperature and under a light load, a mixture with a ratio close to the ideal of 14.7 to 1 ignites readily. However, suddenly depressing the accelerator to increase speed or to maintain speed when hill climbing causes cylinder pressures to rise. This increases the firing voltage needed. The ignition system is designed to have reserve energy available in excess of its normal requirements, so that it's able to produce ignition even when conditions are unfavorable. Most light vehicle ignition systems are of the inductive type. They use an induction coil with primary and secondary windings to step up the nominal 12 volts of the battery to the required firing voltage. The ignition coil is a step-up transformer which raises the nominal battery voltage of 12 volts up to the many thousands of volts necessary to provide a spark across the spark plug electrodes. A standard ignition coil has a rod-shaped laminated iron core, which is located centrally by an insulator at its base. The secondary winding, with 15,000 to 30,000 turns of very thin enameled copper wire, is wound around the core and is insulated from the core by layers of treated insulated paper. The primary winding, with a few hundred turns of much heavier copper wire, is wound on the outside of the secondary. A shield of soft iron surrounds the outer windings, and the complete assembly is inserted into a one-piece steel or aluminium container. The container is then filled with a special transformer oil, which provides good electrical insulation and also permits rapid heat dissipation. The cap has two terminals, positive and negative, for external connection to the primary circuit. The ends of the primary winding are connected internally to each. Provision is also made externally for a heavy insulated center terminal to connect the high-tension coil lead to the distributor cap. One end of the secondary winding is connected to this center terminal, and the other end is connected to one end of the primary winding. A rubber seal and a molded insulated cap seal the assembly in the container, and the container edges are swaged over to bind the coil into a compact, vibration-free unit. The purpose of the distributor is to distribute the high-tension voltage surges to the individual spark plugs in the correct sequence and at the correct instant in time in the engine cycle. Since each high-voltage surge is triggered by the opening of the primary circuit, it is convenient to locate a single set of contacts in the distributor housing and operate them by lobes formed on a cam, which is driven by the distributor shaft. The number of cam lobes corresponds to the number of engine cylinders. Ignition pulses occur as each lobe opens the contacts to break the circuit and then allows them to close, re-establishing the primary circuit in readiness for the next opening. An insulated rotor arm with a brass electrode is keyed to the shaft directly above the cam and rotates within a molded insulated distributor cap held by clips on the distributor housing. The cap has the same number of connecting outlets for the ignition leads as there are engine cylinders, and a central terminal locates the high-tension lead from the ignition coil. An internal spring-loaded carbon brush conducts each ignition surge from the central terminal to the center of the rotor electrode as it turns. By arranging the surge to occur when the rotor electrode is opposite a fixed electrode inside the cap, the high voltage bridges the small gap between them, driving current through the ignition lead for that cylinder and bridging the gap at the spark plug. By positioning the rotor arm opposite the electrode for number 1 cylinder, when it is at the end of its compression stroke, then connecting successive leads in the engine firing order, each surge occurs in the correct sequence. In systems of this type, the distributor is eliminated and each spark plug is fired by a high voltage impulse from an ignition coil shared with a companion cylinder, or by an individual coil specifically for that cylinder. This is referred to as direct fire ignition. In a waste spark system for a 6-cylinder engine, 3 ignition coils, each with their own primary and secondary windings, are combined to form one coil pack. Each ignition coil serves 2 cylinders, with each end of the secondary winding attached by a high-tension lead to a spark plug. These 2 plugs are on companion cylinders, that is, cylinders where the pistons reach top dead center at the same time. The cylinder on compression stroke is said to be the event cylinder, and the cylinder on the exhaust stroke is the waste cylinder. When the high tension voltage is induced in the secondary winding, the secondary circuit is completed by current flowing through the high tension lead to the center electrode on one spark plug, bridging the gap and creating a spark in that cylinder, traveling through the cylinder block, bridging the spark plug gap in the companion cylinder, and flowing back through that high tension lead to its starting point. The cylinder on the compression stroke with its charge of fuel and air is fired by its spark, driving the piston down on the power stroke, while the spark plug of the cylinder on exhaust simply serves to complete the circuit and is wasted. When the crankshaft rotates through one revolution, the roles are reversed and the waste cylinder becomes the event cylinder. Firing of both plugs again takes place, and this cylinder now drives its piston down on the power stroke. This same process occurs on each pair of companion cylinders as they approach the top dead center position. Triggering of the primary circuit in each coil must therefore occur at the correct time in each crankshaft revolution. In electronic ignition systems, the contact breaker is eliminated and switching and triggering of the primary circuit is carried out electronically. In Hall effect systems, a Hall effect generator can be located inside the distributor to signal an electronic control unit to turn the primary circuit on and off. Hall effect generators operate by using a potential difference or voltage created when a current-carrying conductor is exposed to a magnetic field. If a magnetic field is applied at right angles to the direction of current flow in a conductor, the lines of magnetic force permeate the conductor and the electrons flowing in the conductor are deflected to one side. This deflection creates a potential difference across the conductor. The stronger the magnetic field, the higher the voltage. This is called the Hall effect voltage, and if the magnetic field is alternately shielded and exposed, it can be used as a switching device. Hall devices are made of semiconductor material because it produces better effect. In a distributor, the Hall effect generator and its integrated circuit, or IC, are located on one leg of a U-shaped assembly mounted on the distributor base plate. A permanent magnet is located on the other leg, and an air gap is formed between them. An interrupter ring, which has the same number of blades and windows as engine cylinders, is rotated by the distributor shaft, moving the blades through the air gap. When a window is aligned with the assembly, the magnetic field is at its strongest, and its lines of magnetic force permeate the Hall generator and its integrated circuit. This allows the generator to switch to ground the low current signal voltage applied to it. When the interrupter ring rotates so that the blade aligns with the assembly, the magnetic field is shielded from the generator and the signal voltage is not switched to ground. With continuous rotation, the blades repeatedly move in and out of the air gap and the signal voltage will appear to turn on and off repeatedly. This can be used to control the operation of the ignition coil primary circuit. This simplified diagram illustrates the principle of operation. When a blade is in position in the air gap, the Hall generator and the IC are shielded from the magnetic field. The signal voltage is not switched and transistor T0 is off. The base of transistor T1 is positive, and a small current flow through the base emitter allows a heavier current to flow through the collector emitter. This heavier current then flows through the base emitter of T2, and T2 is switched on. Current can now flow through the ignition coil primary winding and through the collector emitter of T2 to ground. This completes the primary circuit and establishes the magnetic field in the ignition coil. With distributor rotation, the blade exits from the air gap and a window enters. The magnetic field at the Hall assembly now permeates the Hall generator and its integrated circuit, and the signal voltage turns on the base emitter of T0. The circuit, now established through the collector emitter of T0, diverts current away from the base circuit of T1, and T1 switches off. Since T2 cannot function without the action of T1, T2 also switches off. This breaks the primary circuit, generating a self-induced voltage in the primary winding, a mutually induced voltage in the secondary winding, and creating a spark at the spark plug. Maximum primary current flow and dwell angle are controlled by the ignition module. With continuous rotation, the primary circuit is established and interrupted as each blade enters and leaves, providing a spark for each cylinder in turn. Ignition advance according to engine speed and load is provided by centrifugal and vacuum advance mechanisms. Engines with engine management systems don't use centrifugal and vacuum advance mechanisms. Precise control of ignition advance according to engine load and engine speed is provided by the Engine Management Electronic Control Unit, or ECU. In electronic ignition systems, the contact breaker is eliminated and switching of the primary circuit is carried out electronically. Optical sensors inside the distributor can be used to sense the crank angle position, and an appropriate voltage signal is then sent to an engine management electronic control module. In this type, a signal rotor plate is attached to the distributor shaft. It has 360 slits at 1 degree intervals on its outer edge. Inboard of these slits are 4 slits, 1 for each cylinder. One is larger than the others to provide a signature effect for number 1 cylinder. As the rotor plate turns, it passes between 2 sets of diodes positioned in line with the slits. The diodes above the rotor plate are light-emitting diodes, while the ones below are photosensitive diodes. When provided with a suitable voltage, light-emitting diodes transmit a fine beam of light. Photodiodes receive this light and use it to make a voltage output signal. When a slit is in alignment, the light beam passes through it and a signal is transmitted to the control unit. When the slit is out of alignment, the light beam is interrupted and the signal falls to 0. The control unit uses the 1 degree signals to gauge engine RPM and crank angle position in 1 degree increments. It uses the signals from the lower slits to gauge the piston position, with the signature slit identifying the number 1 piston. The signals from both sets of diodes are converted by a wave-forming circuit in the lower portion of the distributor body to on-off pulses to send to the control unit. After computing data from the various input sensors against the optimum settings for each operating condition recorded in its memory, the control unit determines ignition timing. It then switches the primary circuit on and off by controlling the operation of a power transistor mounted close to the ignition coil. The power transistor has its emitter connected to ground. The collector is connected to the coil negative terminal, and the base is connected to the control module. A voltage applied from the module sends a small current through the base emitter portion of the transistor to switch it on. Current can then flow from the ignition switch through the coil primary winding and the collector emitter to complete the primary circuit. Once the appropriate dwell period has elapsed, the The module switches off the voltage applied to the base of the transistor, and the transistor switches off the primary circuit. The high-tension secondary voltage is then transmitted to the center of the rotor arm and to the appropriate cylinder. This cycle is repeated for each cylinder in turn. In systems which employ an individual coil for each cylinder, the coils can be placed in an insulated cassette with each coil connected directly to its spark plug. This eliminates the necessity for high-tension leads and reduces the possibility of voltage leakage. Sensor inputs to an engine management control module allows the ECM to determine ignition firing order and to set ignition timing according to operating conditions. Most contact breaker systems incorporate a ballast resistor in the primary circuit. The ballast resistor is inserted in series in the primary circuit between the ignition switch and the positive terminal of the ignition coil. When the engine is running, its resistance provides a voltage drop in the primary circuit, which lowers the voltage applied to the coil. The coil is designed to operate at this lower voltage level and still provide the step-up transformer action needed for secondary circuit operation. However, during cranking, a parallel connection from the starting circuit bypasses the ballast resistor. The voltage available at the battery terminals at this time will now be applied to the positive terminal of the ignition coil. This voltage will give a boost to the current flowing in the primary circuit. The increased current flow strengthens the magnetic field to increase the voltage induced in the primary winding and consequently increase the voltage in the secondary winding. So even under adverse conditions, sufficient ignition energy is available to ignite the air-fuel mixture and start the engine. The high-tension cables conduct the high output voltage generated in the secondary ignition circuit when each ignition pulse occurs. They link the high-tension terminal of the ignition coil, the distributor cap, and spark plugs. Because of the high voltage, the cables are large in diameter and are made from thick-walled insulating material around a central conducting core. The heavy insulation prevents leakage occurring and also withstands the effects of high temperature, oil and moisture. The core of the cable is made of carbon-impregnated linen or fiberglass. It has a specific ohmic resistance value. A crimped terminal at each end provides for connection of the components. The capacitor, also called a condenser, is a self-contained unit which is connected electrically in parallel with the contact breaker. It is made up of two plates, constructed from narrow strips of aluminium foil, which are insulated from each other by a special waxed paper called a dielectric. The plates and insulating paper are rolled up tightly together and sealed in a metal can by crimping the end over onto a gasket. A spring in the base forces the plates and insulation against the gasket to keep out moisture. One plate is connected to the capacitor case and through its retaining screw to ground. The other plate is connected to the external connecting lead. Timing of the spark is normally set at idle speeds by positioning the distributor body in relation to its rotating cam. The timing is set on number 1 cylinder, and the contacts are operated in turn by each cam lobe to provide the same timing point for succeeding cylinders in the firing order. This initial setting before TDC allows time for maximum pressure in the cylinder to be developed just as the piston is descending on the power stroke. However, as engine speed increases, there is less and less time for the mixture to be ignited and for this maximum pressure to be developed. So the ignition point has to be advanced. This must occur automatically in relation to engine speed and engine load. The speed-sensitive mechanism is a centrifugal type, which is located beneath the distributor base plate and rotates with the distributor cam. As engine speed rises, the flyweights on the advanced mechanism are thrown outward by centrifugal force. Since the cam is able to pivot on the distributor shaft, the weights act against their springs and move the cam forward. Under these conditions, the quantity of mixture entering the cylinder is reduced and the air-fuel ratio is set for maximum economy on a lean setting. This type of mixture burns more slowly and therefore must be ignited earlier in the cycle to derive maximum benefit from the fuel. The load-sensitive mechanism is a vacuum advance unit, which is operated by intake manifold vacuum via a port on the carburetor or the fuel injection throttle body. The port is connected by a vacuum line to a sealed chamber on one side of a spring-loaded diaphragm. A mechanical link on the other side connects the diaphragm to the distributor base plate. The base plate is movable and can be rotated in relation to the distributor body in the opposite direction to the distributor cam rotation. The port in the throttle body is above the throttle plate when the engine is idling and no vacuum can reach the advance unit. However, at light throttle openings, the vacuum port is exposed and manifold vacuum is transmitted to the sealed chamber. The diaphragm moves against the spring to rotate the base plate, and since the base plate carries the contact breaker, the contacts meet the distributor cam earlier in rotation, advancing the spark. As the throttle is opened wider, there is less vacuum effect in the manifold and consequently less vacuum advance. At wide open throttle openings, there will be no vacuum advance at all, and ignition advance will be determined solely by the speed-sensitive mechanism. With the primary circuit being switched on and off repeatedly, each coil has to be designed for a particular application so that it operates efficiently. For a 4-stroke 4-cylinder engine running at 2,000 RPM, 4,000 sparks must be supplied every minute. The time available to make and break the primary circuit each time is very short. As engine speed rises, the time available is even shorter. It is very important then to ensure that the length of time current flows through the primary winding is sufficient to create the necessary magnetic field. In contact breaker systems, this brief period of time is the period during which the contacts are closed. This is referred to as the dwell angle. It is usually specified in degrees of distributor rotation. This closed period is influenced by the setting of the contact breaker gap. Once this has been set, the angle remains fixed regardless of engine speed. A large gap gives a small dwell angle. A small gap gives a large dwell angle. The manufacturer's recommended gap provides the specified dwell angle for each application, and the recommendations should be followed. With the ignition switched on and the contact breaker closed, current flows from the positive battery terminal through the ignition switch, the primary winding, and the contact breaker to ground, then back to the negative battery terminal. The current flow establishes a magnetic field around the windings. The field is intensified by the rod-shaped laminated iron core. With engine rotation, the lobe on the distributor cam acts on the heel of the moving contact point at the instant ignition is required. This opens the contacts and stops current flow through the primary circuit. This sudden interruption of current flow collapses the magnetic field, and it returns its stored energy to the coil terminals by cutting across the coil windings. This induces a voltage in the primary and secondary winding. Since the secondary winding has about 100 times as many turns as the primary winding, the secondary voltage can also be about 100 times greater than the induced primary voltage. As the high tension voltage builds up, to the spark plug and across its electrodes to ground. From there, it is completed through the battery and primary circuit back to its connecting point. Opening and closing the contact breaker switches the primary current off and on. When the contacts begin to separate, the primary current tends to flow on and produce an arc across the contacts. The capacitor absorbs this surge of inductive current by providing an alternative path in parallel with the opening contacts. The capacitor charges to the peak value of the primary winding voltage. By the time this has occurred, the gap between the contacts is too wide for a spark to discharge between them. This abrupt interruption of the primary circuit assists in the rapid collapse of the magnetic field, and hence an increase in the value of the voltage induced in the primary and secondary windings. As soon as the secondary voltage reaches a value where it bridges the gap across the spark plug, the voltage in the primary circuit falls to a value below that of the charged capacitor. The capacitor then discharges back through the primary circuit, causing further induction, a continuation of the spark at the spark plug, and another charging of the capacitor. Current continues to oscillate in the primary circuit until all the energy in the system is exhausted. This will maintain the spark at the spark plug for about 2 to 3 degrees of crankshaft rotation. Contact breaker ignition systems provide a simple means of establishing and interrupting the current flowing in the primary ignition circuit. A basic system consists of the battery, to provide a source of energy, the ignition switch, to provide driver control over system operation, an ignition coil, to provide a step-up transformer action, a contact breaker, opened and closed by lobes on the distributor cam as the engine rotates to make and break the primary circuit at the correct time in the cycle, a capacitor, to assist in the rapid collapse of the coil's magnetic field, a distributor, to house the contact breaker and distribute the high tension voltage from the ignition coil and spark plugs to ignite the air-fuel mixture in each cylinder in the correct firing order. Connecting wires and leads suitable for conducting the current flowing in the system at the appropriate voltage level. When these components are connected together, they form two distinct circuits, primary and secondary. In the primary circuit, the positive terminal of the battery is connected to the ignition switch, then to the positive terminal of the ignition coil. A connection is then made from the negative terminal to the contact breaker moving contact point. The fixed contact point is connected to ground at the vehicle frame, as is the negative battery terminal. This allows the circuit to be completed through the frame when current is flowing. A capacitor is connected in parallel with the moving contact and also has a ground connection through its retaining screw. In the secondary circuit, the secondary winding with many thousands of turns of fine enameled copper wire is wound around a central soft iron core. It is connected internally to the primary winding at one end and at the other to the central output terminal, also called the HT or high tension terminal. The central coil terminal is then connected by a high-tension lead or cable to the center terminal of the distributor cap. A spring-loaded carbon brush connects the terminal to the center of the rotor arm or button. This ensures contact is made with the rotor arm at all times, even when the engine is running. As the rotor arm rotates, it lines up with the segment inside the distributor cap, which leads to the spark plug for that cylinder. The contact breaker is a mechanically operated electrical switch which is fixed to the distributor baseplate and opened and closed by the distributor cam with the rotation of the engine. The contacts normally form a self-contained unit fixed to the baseplate by a retaining screw engaged in a slot in the fixed contact. The slot allows for adjustment of the contact breaker gap and the setting of the dwell angle when fitting or servicing. The battery provides a source of energy to supply current to the ignition primary circuit for initial starting purposes. It forms part of the ignition primary circuit and acts in conjunction with the alternator to supply current to the ignition system throughout engine operation. It is also used as a conductor in the secondary circuit, providing a path for the high-intensity current generated across the ends of the secondary winding when the primary circuit is interrupted. Identification of each pair of cylinders and a signal for their triggering is provided by a dual crank sensor fixed to the engine timing cover. This contains two Hall effect switches sharing a central magnet which forms two air gaps between them. Two concentric interrupter rings with a number of blades and windows and mounted on the rear of the crankshaft balancer rotate through the gaps. The voltage signals provided allow the ignition module to identify which pair of companion cylinders must be provided with ignition.
Most automotive ignition systems use an induction coil to step up the nominal battery voltage of 12 volts to the voltage needed to bridge the gap across the spark plug electrodes. These induction coils operate according to Faraday's law. Relative movement between a conductor and a magnetic field allows four ways by which an electromotive force, or EMF, can be induced in a conductor. Move a magnet so that the magnetic lines of force cut across a conductor, as in an alternator. Move the conductor so that it cuts across the stationary magnetic field, as in a generator. Start, stop, or change the rate of current flow in a conductor. This causes the conductor to induce an EMF into itself. This is called self-induction. Start, stop, or change the rate of current flow in a conductor which is positioned close to a second conductor. This is called mutual induction. When any of these methods is used to induce voltage in a conductor, the value of that voltage depends on the density or strength of the magnetic field. The stronger the field, the greater the induced voltage. It is also influenced by the number of turns of the coil. The greater the number of turns, the greater the induced voltage. The speed at which the lines of force are cut also affects the voltage induced. The greater the speed, the greater the induced voltage. In the induction coil, the secondary winding has many thousands of turns of fine enameled copper wire. The primary winding, with a few hundred turns of relatively heavy wire, is positioned close to the secondary. A soft iron core is positioned centrally to concentrate the magnetic field. Current flow through the primary winding establishes a magnetic field around the windings. The higher the current flow, the stronger the field. Sudden interruption of the primary current effectively disconnects the battery from the coil and current flow ceases. This leaves no externally applied voltage source to dictate the voltage value across the ends of the primary winding. The magnetic field decreases, returning its stored energy to the coil by cutting across the coil windings. This produces a self-induced voltage in the primary winding and a mutually induced voltage in the secondary winding. The maximum value of the secondary voltage is partly determined by the ratio of the number of turns in the secondary winding to the number of turns in the primary winding, in this case 100 to 1, and by the value of the self-induced voltage in the primary winding, in this case 300 volts. Then, if this coil is 100% efficient, the maximum voltage available from the secondary winding would be 300 volts multiplied by 100. That is 30,000 volts. Since the value of the self-induced voltage in the primary winding is also influenced by the rate of change of current flow through the coil, it is essential to switch the primary current off as quickly as possible. All ignition systems make provision to ensure that this occurs.
In electronic ignition systems, the contact breaker is eliminated and the switching or triggering of the primary circuit is carried out electronically. In induction-type systems, a pulse generator has a stator mounted on the distributor body and a rotor unit called a reluctor attached to the distributor shaft. The stator has a circular permanent magnet with a number of projections or teeth corresponding to the number of engine cylinders, and a stationary coil of fine enameled copper wire wound on a plastic reel and positioned inside the magnet. The reluctor has the same number of teeth as the stator and as it rotates, these teeth approach and leave the stator teeth, changing the air gap between them. As this occurs, the strength of the magnetic field changes, increasing as the teeth approach, reaching a maximum when they are in alignment, and decreasing as they move away. As the stationary winding is influenced by the magnetic field, then in accordance with Faraday's law, a voltage is induced across the ends of the winding each time the magnetic field changes. And if the winding forms part of a complete circuit, the voltage will cause a current to flow. As the teeth approach, the strength of the magnetic field is increasing. This induces a voltage and current flow in the winding. The polarity of the voltage is said to be positive as it produces a current flow in a certain direction. When the teeth are in alignment, the magnetic field is at its strongest, but at that point it is not changing. Voltage and current now fall to zero. As the teeth move away, the strength of the magnetic field changes again, and once again voltage and current flow is induced in the winding. This time, current flow is in the opposite direction, and the polarity is now said to be negative. Since polarity changes every time the teeth approach and leave the stator teeth, the voltage produced is an AC voltage, and current flow is an alternating current. The coil operates according to Faraday's law of electromagnetic induction. As the high-tension voltage in the secondary winding builds up, a particular voltage level is reached when the spark plug gap suddenly becomes conductive, allowing the spark to occur. This is known as the plug firing voltage. The level of plug firing voltage depends on many factors, such as the mixture density, turbulence, the pressure in the cylinder, the spark plug gap, the condition of the spark plug electrodes, the resistance of the secondary circuit. When the spark reaches the point where a high-intensity current is flowing in the secondary circuit, the voltage drops to a much lower spark voltage level, sufficient to sustain the spark. This gives the mixture the opportunity to ignite during the duration of the spark. The spark plug consists of a plated metal shell with a ceramic insulator and an electrode extending through the center of the insulator. Threads on the metal shell allow it to be screwed into the cylinder head, and a short earth electrode attached to one side is bent in towards the center electrode. The electrodes are of special alloy wire with a set recommended gap between them. The spark bridges this gap to ignite the air-fuel mixture in the combustion chamber. Spark plugs are identified by 3 different features. These are thread size or diameter, reach or length of the thread, heat range or operating temperature. Spark plugs should operate between average temperatures of 400 degrees Celsius and 800 degrees Celsius. This is referred to as the heat range. The temperature that a spark plug will reach depends on the distance that the heat must travel from the insulator to reach the outer shell of the plug and enter the cylinder head and the water jacket. If the heat path is long, the plug will retain more heat and therefore will run at a higher temperature than one with a short heat path.